Welcome to Topic 2B, Solid Material Properties, where we explore the fundamental physics that govern how materials behave under stress. Let's start with a core engineering question. Why do bridges stand under heavy lorries in extreme conditions? Engineering is the art of ensuring materials can withstand extreme conditions, from storms to overloads. We need to choose materials that won't fail when needed most. Today, we'll explore the physics of solid materials, how they stretch, squash, and why they eventually break. This is crucial for all forms of design and construction. We begin with the basic relationship between force and deformation, Hooke's law. Robert Hooke discovered that for many materials, the force applied is directly proportional to the extension. The constant, K, is the stiffness or spring constant. This law applies to both tension, pulling apart, and compression, squashing together. Hooke's law only holds up to the limit of proportionality. Stay below the elastic limit, and the material returns to its original shape. Go beyond it, and the material undergoes plastic deformation, permanently changing its shape. When you stretch or compress a material, you are doing work. Where does that energy go? It's stored as elastic strain energy. The work done to stretch a material is stored as elastic strain energy, following the formula shown here, provided the relationship is linear. On a force extension graph, this energy is simply the area under the line. If the relationship is non-linear, we must estimate this area by counting squares or by splitting the shape into simpler geometric figures. Now let's look at concepts that allow engineers to compare the fundamental stiffness of different materials, regardless of their size. To compare different sized objects fairly, we use stress and strain. Stress is force per unit area, measured in pascals. Strain is the extension per unit of the original length, and because it's a ratio, it has no units. The Young Modulus, E, defines the stiffness of a material itself, regardless of its shape or size. It is the ratio of stress to strain in the elastic region. This value is critical for selecting the right material for any application. The stress-strain graph is essentially a material's biography, showing exactly how it responds to increasing force. The initial linear section shows the limit of proportionality, followed by the elastic limit. Up to this point, the material behaves predictably. Beyond the elastic limit is the yield point, where atoms begin to slide. The ultimate tensile stress is the maximum stress before it drastically necks, and finally, the fracture point is where it snaps. How do we measure these values in a laboratory, and what happens when materials don't unload the same way they load? In the lab, we measure the Young modulus by stretching a long, thin wire. We use a micrometer to measure its diameter, and a ruler or vernier scale to measure the extension as we add mass. Safety note: always wear eye protection. Some materials, like rubber, don't follow the same path when unloading. This resulting loop is called hysteresis. The area between the loading and unloading lines represents energy transferred to thermal energy, which is why a rubber band feels warm after repeated stretching. These properties are not just academic, they are essential for safety and reliability in countless applications. Physics saves lives. Climbing ropes are designed for high dynamic elongation to absorb the impact of a fall. By engineering for the correct Young modulus, manufacturers ensure the force on the climber and their anchors remains within safe limits. Mastering these properties allows us to build skyscrapers, design safe cars, and explore the limits of material science. Keep practicing your unit conversions and graph analysis to apply these concepts effectively.